thing. Okay. Okay, we are back. Right. By the way, actually, when I was logging in, you see that this one, my camera is actually closed because I actually put a cover. So actually, because nowadays we don't know who's going to hack our webcam. Okay. So when we are online, only we open but if we don't have online, then we close it. So we know that it's not going to capture. That's not. I think for the girls, especially again, not wearing the hijab. Okay. So we continue. Screen. Right. So we were here, right? Okay. So we were talking about the how to actually write out this one. We have the tank draw out first of tank, and then we have this equation P1 minus P2, okay, equivalent Kp dot F. So that's why you have Kp actually is the resistance, okay, inside the piping. So we have this resistance. So that's why you have the resistance. And then P is that you have the pressure P in. So pressure P in is that you can actually put it as the pressure source. Remember that in the previous comparison, with the electrical system is that you have V in, the voltage source. So it's same thing. P in is actually the pressure source. Okay, so that's why this diagram, you can actually plot the schematic, become P, the pressure source, and the resistance. You have the tank, and then next is that you have the resistance again at the flow out. Okay, so this is how you're going to actually do the mathematical modeling for a simple tank, and how to do the diagram, to draw the diagram. Next, we're going to go for the thermal system, okay, and how to model the do the modeling. So we are going to first go to introduction of the energy storage with temperature. So let's see is that we are going to consider heating system comprising simple storage and energy. So you see here is that you're talking about fluid system, which we have a tank. So it means that we have a storage, which is the water bottle. We store water, and that's why we have the energy, okay, the pressure at the bottom. So similar to the temperature system, we actually can have the energy flow and also storage. Okay, so how we are going to show it analogous behavior to the LC circuit is that, let's say that we have a thermal energy stored is linear in temperature. So we have a medium. The medium is like a material, steel, example, made from steel, solid steel. So you can actually measure what is the energy stored in that material. Q is energy stored, equivalent to C is the thermal capacitance, okay, dot T, temperature. Okay. So this one is the idea, the general equation. Okay. So similar to the fluid system, we are going to look at how does the heat flows through a medium. Okay. So we have first one is that the heat flow will be in unit joules per second or power watts. So it means that it's going to have a medium here, okay, and then you will have a heat flow moving through the medium. We have different temperature on each side. So we have temperature, for example, this one is a medium. We have temperature T1 and T2. Okay, can you imagine that? No. Imagine that you're actually in a cool environment. Okay, in an aircon environment, temperature is 16 degrees. It's cold. You're not wearing any sweater and so on. So it means that the temperature, your temperature is actually temperature T2. Okay, your body temperature. T1 is actually the environment. Okay, so it means that if you want to actually reduce the field your temperature to increase your temperature. So what you need to do is that need to add another layer. Okay, you're going to wear sweaters and so on. So you are going to actually wear this. Okay, this one will be your sweater. Okay, heat flow from temperature, the environment, to your body, T2. So this one will be the heat flow. Okay, so it depends on the material that you're going to use. If you wear only cotton, then you'll feel cold. Okay, but if you wear wool, then you're going to have insulation. Okay, so assume that a cross-sectional area means that this cross-sectional area will be the same value from this part until this part. Similar to the tank just now. Tank is that you have the height. We're talking about the cross-sectional from top to bottom is the same value. But right now we are talking about the cross-sectional. If this one we cut, this is cross-sectional of my sweater. Okay, cross-sectional of my sweater, which is zoom view. This is sweater, cut off. So heat flow from the temperature, the environment to your body. So this is the cross-sectional. So of course, your sweater normally you will have the same ketebalan, same width lah. Okay, same, what was the word? Same ketebalan lah, Same what?
Thickness.
Yes, okay. Same thickness. Okay, so if you have the same thickness, we assume that in this equation, so heat flow is created by temperature difference between two ends of the block. Okay, if for example, if you have T1 and T2 is the same, does the heat flow through? No, it's going to have a steady state, right? It's like a closed loop plot diagram. If the end output value is compared with the input, if it's the same value, error is 0, then there's no flow, there's no comparison. Okay, so heat flow is only created if you have a difference between two ends of the block. Okay, so we are going to in this, if we are going to assume that the steady heat flow, which is W, which is proportional to a constant which depends on cross-sectional area, cross-sectional here, and the conductivity of the material and temperature differences. So from here is that equivalent, similar to the fluid system just now, we are going to do the first equation. So T1, temperature at T1 minus temperature at T2 equivalent to KH. KH is constant value of the medium here. Okay, dot W, which is the heat flow rate. Okay, so this one will be the first equation. Next is that we're going to represent the thermal system in a single medium. Okay, single medium means that you have only one material. Okay, let's say that like in Japan, people during winter or during autumn or spring, what they do is that they do layering of cloth. Cloth, the jacket. So they wear a t-shirt, then they wear another sweater, then they wear another double sweater. So different for fashion basically. So that means that they are going to have a two medium in between, means that two layers of different material. But this for this slide is that we are going to do, first one is for single medium. So assume that we have an item that has thermal capacitance C, okay, and temperature T2. So we have a medium here, okay, T2, which is temperature T2, and then we have the thermal capacitance is C. Okay, it is insulated from the environment, means that you're putting an insulation there area, okay, with a temperature T1. So this one is the first layer, T2, and then we have a layer of T1, which is insulation. So the insulation layer is T1. Okay, so it becomes like a blanket if resistant to energy flow from this area. Okay, W, which is the temperature flow just now. So from T1 to T2, we have the flow, energy flow, the heat flow. So if you were to actually draw again this analogy, okay, we can draw it as this. medium, one medium. Okay, from T1 is going to move to T2, and you have the heat flow in this direction. Okay, using the equation Q equal to CT2, so we are going to do the equation for the medium T2. Okay, so Q here is equivalent to CT2. So we get dQ, okay, differentiate Q, we get C dt2 over dt. So it means that the differentiation of the temperature there. Okay, first equation. Second equation is that we have the heat flow equation. T1 minus T2 equivalent to KH. This is value of KH dot W, heat flow. So you get the second equation. So substitute the equation. We know that W is actually the differentiation of the energy flow just now. So you have KH dQ over dt equivalent to T1 minus T2. Okay, so KH is C, substitute this one. Okay, C d2 over dt, T1 minus T2. Next is that you get, arrange it, you will get the final equation as this one. Okay, you want it to have the T2 terms on the left side and T1 is on the right side. Means that T1 will be similar to like an input voltage V1, just not voltage source. Okay, so this one looks like a first order differential equation. Okay, so this is how you model a single medium. Okay, so the analogous term of a thermal electrical quantity can be shown below here. So the voltage source, voltage supply is analogous to T1. So means that T1 is analogous to V1 as to V. Energy stored in a circuit is analogous to the Q squared here. Okay. System thermal capacitance is analogous to capacitor. So means that it's the same thing, 1 over C, 1 over C. And insulation is analogous to resistance. So insulation here, okay, D2 over D2 is actually analogous to resistance. Okay. So this slide just show the analogous summary of all electrical, mechanical, and also for the fluid and thermal system. Okay, so fluid we have thermal, we have RLC, and then we have mechanical. So this one is just analogous so that you can compare in one slide. So let's see is that what is the impact of adding more medium in series. Just now is that you only have one medium. Okay. So what is the impact if you have two medium in series? So if one medium is placed next to another block, so you have one block here, you have T1, T2, is flowing, the heat flow is going to the left side. So what happened to the modeling of the system? So if you were to add another medium on the right side here, so you have the flow for KH2 is from T2 to T3. Okay, heat flow will flow from T1 to T3. Okay, so here is that we are going to assume that the same heat flow through both medium when it's in series. Okay, so what you need to do is that you're going to find out what is the equation for the flow, the heat flow for KH1 and KH2. So you can write it as this one, T1 minus T2 equivalent to KH1W, okay, for first equation. Then for the second equation is that T2 minus T3 equivalent to KH2W. Because here we assume that the heat flow is the same, that's why you have W is the same value. So substitute that, then rearrange it, then you can actually get this equation. T1 minus T2 equivalent to KH plus KH2W. So this one is that when you have medium in series, we can make a summary is that the resistance to heat flow is increased and hence this is not us, is discussed. So the power will be reduced. Okay, so similar to the single medium just now, try to derive, because just now was to derive only for the single medium. So try to actually do this derivation, okay, until you get the equation of the first order differential equation for the two medium. Okay, for this one is not the final answer yet, so derive it so that you get the first ODE, first order differential equation, okay. Just do it later on. Okay, we are going to go to the next example of a thermal system with an external heater. Okay, let's say that you have a thermal system medium T2 with temperature C. If it's insulated from environment of temperature T1 with blanket, not blanket, typo, blanket if resistant to energy flow KH. So we are going to add some external heating at rate omega 1. Okay, so the heat flow here is W1. Sorry, not W1, W only. So you have T1, T2 outside here, temperature, the environment temperature. So find a model for the temperature of the system. So let's do the first equation. Get the equation for Q for T2. So Q equal to CT2, dQ over dt, you get this equation. Then next is that you get KHW equivalent to T1 minus T2. Okay, done. So what you're going to do is that you're going to rearrange this equation, become dq over dt equivalent to T1 minus T2 over KH. Now you're going to add the external heating, okay, omega W1I, external heating. So when you rearrange it, that what happens that you have on the right hand side is that T1 over KH means that the source, which is actually the temperature T1 environment over the constant value for KH plus the external heating rate omega 1, omega I. Okay, so this is the difference between if you don't have an internal heater. If you don't have this, then this is not available here. But if you have an internal heater, then you're going to have the value Wi here. Right? So analogous in an electrical system is a current source, omega 1 I. Okay, so actually you have here is adding a current source. Okay, as a summary is that, okay, when medium is placed in series, so the overall resistance to heat flow increases, so heat flow reduces. Means that when you add on several layers of material in series, then heat flow will reduce from end to end. Okay? So resistance in series add to give total resistance, so you can actually add the resistance KH1 plus KH2 plus KH3 equivalent to the K equivalent. Then third one is that simple thermal system with two different types of input. So what you did just now was you actually try to add external temperature to a thermal system, and you direct heating it at the Wi there. Okay, so you get two different types of modeling. Okay, and the last one was that you showed that model have a simple analogy with series resistance, capacitance, and also to the mechanical and RLC circuit just now. Okay, so that's a summary. So any question? We're actually at the final point of our slide before we go for quiz. Any question? No? Ain?
No.
Any? No? Zameh?
No question.
Arif? Again?
No.
Eba? No, Alright, if no, we take a break. I think now we are on, how many minutes? Okay, anyway, we take a minute for 5-minute break before we start with quiz. So we are going to have a 30-minute quiz. Okay, what you need to do is that take out a piece of paper. Okay, piece of paper, and then okay, those who are roommate Arif and siapa Kugen Arif and Kugen, don't talk please make sure that your webcam is live so I can see there's no talking. 30 minutes. Later after we enter back again into the session, then we will start quiz. So right now is 10:04, so we come back again at 10:15. Okay, 10:15 to start our quiz. Alright?
Okay.
So see you.